Okay, good morning, everybody. Hopefully you can hear me. If possible, just somebody in the chat. Just verify that you can hear me and see me. Okay, thank you very much. We can hear you. So let's start. There's a few announcements here posted on Canvas. The calendar of dates is posted under course information. Dawn is updating the suggested readings, so please do keep monitoring them and reading at home. Exam info is posted. We will try to very shortly get up information about exam 3 coming up next week. And please bear with us and give us some patience. We understand that this is a new situation for you, and we'll try to make this as, non-stressful as possible. And then the grades have been updated as of 3/29. So that's the first bit of announcements. And why is my, okay. So the second thing that I'd like to share is not quite the notes yet, but hopefully I have, where did this go? Thanks for bearing with me as I get my sea legs again on this. Okay, so when we used to have lecture in Demerit Hall, in the first 10 minutes or so, you were free to talk to your colleagues, and I encourage you to do that before and after class. I'm fine for you to do that. Our exam is next Tuesday. It's going to be on ray optics, optical elements, and electrostatics. And please, we'll post details of how this is going to be implemented very shortly. Some small fraction of people were not able to access the videos, and for that reason I started a YouTube channel, Physics-Slifer, where you can get the videos if you're having trouble getting them from Canvas. And the last thing is, if you want to get office hours with me, office hours quote unquote, we'll do it through Zoom, but just email me to schedule that. I'll flash this up for a moment. It'll be in the recordings, and then I'll post it. This is my general availability, so wherever this is hashed out is not going to work during the week, but the open spaces would be fine, and I'm happy to do office hours that way if you so wish to do. So let's start. I'm going to start where we left off last time. Hopefully you can see my notes. And the notes now are posted on Canvas. So I hope that you can also have a copy of these in front of you if you have any trouble seeing them through the Zoom link. The last thing that we talked about was superposition, and we did a one-dimensional example of that. We saw even in this one-dimensional example, it was quite subtle, and there were some places where we could get tripped up on solving these problems. I hope I walked you through those, and I hope you're getting more comfortable with those. I introduced the idea of an electric field, whereby we bring a charge into a region of space, and that charge alters the space around it in some fundamental way with an electric field. And then if I bring in a second charge, that second charge is going to feel the electric field, and that electric field will exert a force on a second charge. So this is a new way of thinking of things. Once we have that electric field, we can determine what the force on a charge in that electric field is by just multiplying that charge by the electric field. The one thing I don't think I mentioned last time was the weird units of electric field. And the units for this to come out right is going to be newtons per coulomb, right? If this is newtons per coulomb and charge is in coulomb and SI, my force is going to come out in newtons. So it's a bit weird, but that's our units for electric field. we also talked about the electric field of a point charge. Whenever I do this E with an arrow on the top of it, that's going to, that's shorthand for saying electric field. If I don't put the arrow on top of it, I'm talking about, I'm talking about the magnitude of that electric field. It's simple enough to calculate. If we have a source charge Q, and I know the distance to the point in space where I want to determine that electric field, right? Our source charge is over here, and I say, hey, I want to know what the electric field is at this point. I just measure the distance from the source charge. That's my R squared in the denominator. K is my Coulomb constant. Q is the magnitude of this charge that I plopped down in space and is causing this electric field in the first place. It's my source charge. So let me get some of this stuff off my desktop so I'm not distracting you. So that is how we get the magnitude. And we looked at a few simple examples. If I have a point positive charge, right? So I come in here with a point and it's positively charged and I place it in space, it's going to create this electric field. We started trying to draw these electric field lines. I'll give you the rules of drawing these electric field lines in just a moment, but let's look at the examples that we did see before. I have this positive charge and the electric field lines radiate out from that positive charge, and we're to envision that these go to infinity, right? They go on forever. Why? Because we have a 1 over r squared in the denominator. This r, as far as we can get away, this gets bigger and bigger and bigger, so this electric field gets smaller and smaller and smaller, but it never goes to 0. So we're to envision that this electric field goes forever and just gets weaker and weaker and weaker and weaker. In practical terms, usually you get a foot away from a charge or something like that, and the electric field has died off to the point where you can kind of neglect it. But it never quite goes to 0, and that's what we're trying to signify by these arrows going off to infinity. The second part that's interesting about this is if you look at this, the closer we are to this positive point charge, the closer spaced these electric field lines are. And that is on purpose. The density of lines, how closely packed together the lines are, is supposed to signify the electric field strength. And again, this is reflecting that 1 over r squared nature. When we're close to the point charge, that r is very small, the electric field is large. And as we get further and further away from that point charge, the r becomes larger, the electric field dies off, and we get less densely packed electric field lines. Okay, so that's our electric field of a point charge, a positive point charge. Similarly, we looked at a negative point charge. All these features that I just talked about are manifest here, slightly different way, but the same basic principles. We have our negative charge. The electric field lines are ending on a negative charge in all of these cases. That's going to be one of our general rules we'll see in a moment. The density of lines is closer as we're closer to the point charge because the electric field strength is stronger in that region. The further we get away from it, the less densely packed these are, the less magnitude of electric field that we have. I'll write all these rules down in just a moment, but let's take a look at our 3 examples. Our third example, which was slightly more complex, I showed you this in terms of pepper in floating in oil and a positive and a negative point charge. This is a general charge distribution that we call the electric dipole. And what we're supposed to think of here is we have a positive charge at this point in space separated some distance away from a negative charge. And for whatever reason, they're not free to move further away or closer together to each other. You think of them being on the edges of a rigid rod or somehow glued at their distances from each other. So they have the ability to move as a team, but they can't get any closer, they can't get any further. And this is what's known as a dipole electric field. The electric field is some combination of these 2 electric field diagrams that we saw up here. And you can see that the electric field lines are originating from the positive and flowing over to the negative. Never in this do we see the electric field lines cross. That's another general feature. And we see electric field lines coming in and terminating on that, that negative charge. So again, we have a slightly more complicated electric field map here, but the lines always start from positive and they go to negative. They never cross over each other, and they indicate the direction of the electric field. So with all that being said, I'm gonna pause in a moment and ask for questions. But the idea here is stipulated in these four simple rules. Our lines start on positive charges and they end on negative charges. The one caveat to this is that the start or the finish of the electric field lines can be at infinity. So if we go to these guys, to this guy right here, we start on a positive, we head off, and you're to imagine that these extend forevermore in all directions off to infinity. The same with the negative. Here we would be imagining that these are originating some huge distance away, and they land and they end on a negative charge. The same here, we start on a positive, we end on a negative. Okay, so that's our first rule, is that our lines are going to start on positive, they're going to originate on positive charges, they're going to end on negative charges. The direction of the arrows indicates the electric field direction, and more importantly, this is going to indicate the direction of the force on a positive charge. Bear with me and let's take a look at our three examples here. So going back to the positive charge, what does this mean? I have to get my little annotator, my drawing tool up on this. And if I come in here and I put a positive charge at this point in space, right? This is some positive. Can I draw a positive? Okay. What's going to happen? This positive charge, because this is a positive charge, they repel, right? Going back to our understanding of electrostatic forces. Like charges repel each other. So this is going to want to get away. It's going to move along that electric field line and move away from that positive charge. So if I come in with a positive charge, it's going to want to move along any one of these electric field lines away from that source charge. If I do the same in my next configuration and I come in with a positive charge, here, this is a little bit of a bigger marker, and this is positive, sorry, it's a little bit, there you go. Positive charge, what's going to happen? This is going to want to get away from I'm sorry, what am I doing? I'm not thinking straight. I'm not thinking, forget that. Sorry, let me do this again. So I come in with my positive charge, right? I put my positive charge down here. What's it going to want to do? It's attracted to that negative charge, so it's going to move in this direction. My apologies, it's early in the morning and I'm making a stupid mistake. It's going to move along the field lines and be attracted to that negative charge. So that's our next rule of drawing electric field lines. And in the comments, please do ask me a question if my mistake there confused you. The next part of this is lines are closer together where the field strength is stronger. Again, as we're closer to those source charges, the density of lines is higher than it is when we get farther away. And that is just reflecting this 1/r² magnitude of the electric field. And the final thing is, we don't want electric field lines to cross. The force must be unique at each point in space. If we are drawing electric field lines, the force is just proportional to that. It's going to be pointing in the exact same direction. So if I had an electric field line that crossed another electric field line, say like this, if I had another electric field line that was going like this, then at this point right here, that charge, if I put a positive charge at this point in space, it would experience a force this way, and that would not be a uniquely defined force. We want these electric field lines to tell us exactly what's going to happen if we put a positive charge in that electric field. So we can never have electric field lines cross. That's the last rule of this, this graphical way of representing electric fields. So we can put a lot of information just in these little cartoons, and if we kind of digest these rules and implement them while we're drawing electric fields. So I'm going to pause. I hope that you can ask me some questions before we move on to the next topic. And if you don't have any questions, that's okay too, but I don't want to rush you through this.
For field lines crossing that they can never cross, isn't that kind of, I don't know, unnecessary to say? Because it's not like there are actual lines, right? And within the field, it's just kind of a general presence of charge in a direction. Or is it for, like, in terms of drawing, you should never draw it so that they cross?
You should, so yes, you should never, again, this is a graphical representation. It's not, it's a limited qualitative way of representing this very quantitative, specific way of calculating the magnitude of the field. I'm not sure if I quite understand your question. I'm going to try to answer it. You got to be honest with me. If I don't answer it, please push back and ask some more. But the point here is we're trying to represent this electric field graphically. And if I had an electric field line at some point in space that crossed over another electric field line, then at that point in space, I wouldn't know what the electric field was in this graphical manner. Because the electric field would point in two different directions, and I just don't want to do that. Every single point in space, no matter what the charge configuration is, we're looking at very simple charge configurations right now, a point particle, for example. But anything that you can imagine, any weird configuration of charges, no matter what, once everything settles down, the electric field is going to be uniquely defined at each point in space. And if these electric field lines, if we draw them, if they crossed over each other, then at that intersection of those two electric field lines, it would not be uniquely defined. It would say, hey, maybe the electric field is pointing this way, maybe the electric field is pointing this way, I don't know. So we want to just avoid that and say, never, never, never draw it that way, because in nature, the electric field is always uniquely defined. Does that help, Sarah, or did I not answer your question?
No, that was exactly right.
Okay, thank you for the question.
Yeah.
All right, so where did we talked about electric field lines here. The next thing that I'm going to move on to is conductors and electric field. But just as we normally do, I'm going to stop the recording momentarily and move on to our next topic at a logical point. So I'm going to stop this recording. It has no impact on you guys. Let me